Hello, everyone. Welcome to this week's Crunch seminar. Today we have one speaker. His name is Thivin. He is a PhD student in Professor Sashikumar's lab. Professor Sashikumar joined the department of. First of all, Professor Sashikumar and Thivin, welcome to this seminar. And could you please try sharing your screen? Great, and maybe you can put it in presentation mode. Great. Okay, now let's start again. Okay, hello everyone. Welcome to this week's Crunch seminar. Today we have one speaker. His name is Thivin Anandh. He is a PhD student in Professor Sashikumar's Ganesan group. Professor Sashikumaar joined the department of CERC as an assistant professor in 2011. And before joining the department, he was a research associate at the Imperial College London and an Alexander von Humboldt Fellow at WIISc Berlin. He had more than 15 years of experience. He had more than 25 students and have worked in more than 750 working professional upskills on artificial intelligence and machine learning. His research interests include finite element analysis, high-performance computing, data-driven modeling, cloud computing, scientific machine learning, AI, and MLOps at scale. He also heads the Scientific Machine Learning and Operations Group at CDS. He has more than 50 journal publications. He's the co-author of the book Finite Elements, Theory and Algorithms from Cambridge University Press. Thivin and Professor Sashikumaar, with this short introduction, you can start whenever you're ready.
Yeah. So, hi, everyone. So thank you for introducing Professor Shashi. So I'll briefly introduce myself. I'm Thivin. I'm a PhD student working under Professor Shashi. So today we will talk about the FastVPINNs framework, which is just a tensor-based variational physics-informed neural networks for solving problems in complex geometries. Okay, so the idea of how this presentation is going to go today is like we will introduce a very basic idea on what pins and variational pins is, what are its differences. Then I think what is the current state-of-the-art implementation of HP variational pins framework is. We'll try to understand what are the improvement areas in those framework and what did we target and what did we achieve out of it. So what algorithm made our implementation faster, and by faster, we would like to quantitatively compare the execution times of the previous implementation and the current implementation. Then we'll slowly move on to the applications where we solve problems, both forward and inverse problems for scalar problems in regular and complex geometries. And we'll show some of our slides on where our work is progressing towards in some of the examples on fluid flow problems. Okay. So again, I don't think this group needs much of an introduction on what PINs is. Physics-informed neural networks is a special kind of neural network where you get the solution from your neural network, and for your given spatial or time coordinates, you use automatic differentiation to obtain the gradients of that particular solution with respect to the inputs, which generally turns out to be the terms in your PDE. You use those terms as one of the laws, the residual as a loss in your while training your neural network. You also add some of the supervised loss in terms of the boundary components and its boundary values, and you have a neural network which is trained to predict solution at any spatial point or a time in a time dependent problem in any time step for a given PDE trained for a given boundary condition. So variational physics informed neural networks is also similar to PINs. The only difference being the fact that the loss function which we saw in PINs, so let me try to take the laser. So the loss function which we saw in the PINs was in strong form. However, if you look at methodologies such as finite element method and so on, so we are used to the other form of the loss function or loss or the governing equation, which is called as the variational form, where we multiply the equation by a test function and integrate it over a domain. To put it simply, we try to search our solution spaces restricted to the space spanned by the test function that we are trying to set up in our domain. So in variational pins, instead of using the strong form of the equation, we tend to use the variational form of the residual for training. So couple of challenges that might immediately pop up is how do you evaluate this integral, and what kind of test functions when you say that can be used. Again, so integral evaluation that can be done using numerical quadrature routines. And then the choice of test function generally depends on your problem. The most commonly used are either legendary polynomials or Chebyshev polynomials, or to be in a broader class, any form of Jacobi polynomials. Okay. So before we get into it, so this FastVPINNs framework is entirely an optimized application of HP variational pins, where H stands for your H refinement, where instead of having a single set of your test functions spanning your entire domain, you restrict the domain to which your test functions are supported, so that you have multiple sections of this. So that forms your H refinement, and your P refinement is generally increasing the order of your polynomial to capture, let's say, more higher order frequency within your domain also. Okay. So moving on, what are the primary advantages of using a variational formulation? There is a strong formulation which obviously works. And what is the need to, let's say, go to a framework like variational pins to do this? One a good thing that immediately pops up is that it reduces the differentiability requirement of your neural network. So one thing that people in finite element framework that generally does is that they perform integration by parts once they write the residual in its peak form. So when you do integration by parts, you can transfer one of the derivative from your actual solution to your test function. Since your test function is known, these derivatives can be pre-calculated and they don't have to be calculated again and again. And what it does to our variational form is it reduces the differentiability requirement of our network, which means instead of now having to do two propagations to calculate the second derivative of the solution, you just need the single derivative of the solution. Second thing is that pins being relatively new in terms of, let's say, trying to compare it with traditional methods, we are still building all the mathematical foundations in trying to understand the convergence and everything of pins is there. Again, so trying to do in terms of variational sense, where we generally do in FEM and other numerical methods, we can try to bring some of the insights that might have worked while trying to solve certain PDEs using these frameworks, and these can be try to implement. We can try to use those knowledge in trying to solve these problems in future. Okay, so what are the advantages of using H&P refinement? So again, so the ability to localize your test function to a smaller region will help or aid the network in capturing higher frequency solution. So this can alleviate the problem that generally occurs with pins in trying to, let's say, solve higher frequency problems. So this loss graph shows the effect. So where you have a single problem, your left-hand side graph shows increasing number of test function and the errors predicted for it. And the right graph shows you the number of elements that are being increased in the domain in such a way and the accuracy obtained for the same. Again, this is just the introductory example that has been taken from Kazmi et al.'s paper on HPV-PINs. And so this is the introductory on the need to use HPV-PINs for solving your problems. So let's go through the current state of the current implementation of the algorithm is. So if you look at the algorithm, your domain is divided into a lot of subdomains, as you are seeing here. So what it generally does is it's similar to how you assemble your loss matrix in FEM. So you loop through all the cells, and what you do is then you get the solution at all the points within that cell. You compute the gradients, you compute the Jacobians from your FEM routines or whatever it is. Then you have the integral. When you convert it into a numerical sense, you have a loop for the number of quadrature points, and you also have the test function loop. So these are the three loopings that mainly dominate the calculation in our HPV-PINs. Then we calculate the residual for the cell, and then we keep on appending them until the losses for all cells are computed. Then we try to add it to the Dirichlet loss to train the final equation. So one thing to notice here every time is that, So let's say for a domain, which is composed of n cells, let's take 100 cells for example. You need to do a forward pass of 100 times, which means like for each cell, you have to do a forward pass. So which will get to 100 forward passes for a single training epoch. And if you know forward passes doesn't consume much of the time, the thing that takes most of the time is where you compute the gradients for your for that for the forward pass that you have performed. In this case, the gradients of the solution. So in this kind of algorithm, when you have a number of cells, you will have to perform this gradient calculation n number of times separately. So that is the main factor that was influencing the speed of HP variational pins. Because if you see on the right hand side, this creates a lot of dependency of on the number of cells on the training time for variational pins. So let's take a simple example. We have playing that you can divide your domains into larger subdomains to enable the network to capture higher frequencies and so on. So but let's take for an example, let's take a 6,400 quadrature point um, uh, system where you solve it on pins. Obviously, you will get same iteration time. So you solve it for 6,400. Let's record the training time for per epoch is. But now what I will do is I'll put all 6,400 points in one cells. And here I'll split them into 4 cells and like equally each cell will have 1,600 points and so on. So here you can see at this point and this point, both pins and variational pins had the 6,400 points, but this has 400 cells. That points are divided into 400 cells. So whatever the advantage that HPV-PINs brought in was overshadowed by this algorithm, which asks it to, let's say, calculate the gradients n times, which increases the training time linearly, even though the global number of quadrature points is conserved. So that doesn't give us a very strong or a comparative metric to compare it against an existing implementation like pins. So that's where the first motivation to, let's say, address this problem comes in. Second thing is that the current implementation is set to work only for the quadrature cell, simple quadrilateral cell, where your quadrilaterals are non-skewed or anything. So there, the idea is that the Jacobian of that could be easily calculated from affine transformation, which is a simple calculation to get the scaling of your cell when compared to your original cell, because all your reference calculations are done from a domain of -1 to 1. You need to transfer them back to your actual cell. So that calculation becomes simpler when you have geometries like this. However, when it goes to a skewed geometry, where you have skewed quadrilateral cells and everything, which obviously occurs in a lot of real life applications, this kind of approach needs to be improved a little bit. Okay. So what are the proposed improvements that we need to do? So first thing is to address the complex mesh. Again, so we are from an FEM background. I spent a significant amount of time solving writing FEM high performance finite element codes on GPU and for distributed computing. So we know from FEM that we handle complex meshes generally using the transformation that we generally use is bilinear transformation, at least for the quadrilateral cells in 2D. So we decided to use that. And the only thing that comes out is that you need to have routines which can, let's say, read an external mesh, and similar to how you set up all your shape functions and everything, your transformation routines in FEM, you need to write additional modules in your code so that it can handle these things, so that it enables us to solve problems in, let's say, geometries like this, which is currently a limiting factor in the implementation of the code that's available. Second thing is that when these trainings run on GPU, it is always, whenever something runs on GPU, it's always recommended to use a blast routines one way or the another, because considering all the routines that's available, and like even if you try to write a highly optimized thread divergence free routines, blast routines have a very strong history in trying to optimize this calculation, in trying to extract the last bit of performance from your existing hardware implementation, since they have a huge history of development going behind that. So whatever we tried was to somehow implement a blast based routine into this calculation so that we could make this faster. The first thing that we try to do is that we try to vectorize the cell-wise calculation. So when I say vectorize, this part of the thing. So if you can see here, at every test epochs, this calculation of Jacobian, this multiplication of Jacobian with weight with respect to your test function does not change. Only the gradient produced by your neural network at each of the element changes with every epoch, because the neural network has learned a new solution, so that it would have learned a new gradient too. So what we did is we assembled all the components, your Jacobian, your quadrature weights, and your test function into a matrix of size n test and n quad, and we saved it, because since it does not have to be calculated again, then we multiply it with a vector of gradients from your neural network to generate the loss for a single cell. Again, even in this, the cell-wise looping still exists, but what we are trying to achieve is that the second loop calculation that we have seen before to, let's say, compute the PD loss in a cell has been converted into a single blast operation, a matrix vector routine, where the matrix need not be calculated. It can be saved once for a cell and then reused across, let's say, 100,000 epochs of your training or so and so. So that kind of provided us 20% of improvement when compared to your normal implementation, especially when your number of cells grows higher and higher. What we observed is the utilization of GPU getting improved when we try to calculate loss in such a way, because when you again obviously use a calculation like a matrix vector routine, your the amount of calculations performed are always optimized, and you will be able to get the results faster. So again, this does not still answer the question of your cell looping, which turns out to be the main scaling factor when you go for higher number of cells. So what we observed is that, so let's say when we use a cell with a simple geometry, let's say these cells, where all these cells have a property such that if you calculate the Jacobian of them, the diagonal components will go to, the anti-diagonal components will go to 0, which means they generally will have a constant value of Jacobian, which is just to scale the value from a reference domain to your actual domain for each of your quadrature points and so on. So what we realized that was, like, previously we had our single reference gradient matrix, which is dou v by dou x, which is n test cross n quad. And this will be pre-multiplied by Jacobian in our previous optimization that I showed here. But what did we observe that was, since a single Jacobian or a Jacobian until the dimension of your number of quadrature points, multiplying that can change this reference gradients into an actual gradient. So what we decided to do is, we decided to save only the reference gradient of all cells as a single matrix, and then we assemble a separate Jacobian matrix for each of the cell column wise. Okay, so once this Jacobian matrix is constructed, and then we get the gradients for all the cells in our domain, which means, so let me try to draw something here. So if you go there, so previously we had this calculation going for each of the cell, and we will loop through them to find it. But what we'll do now is, we'll concatenate the input of all the cell into a single vector or a single dimension. So let's say in 2D problem, it will be n cross 2, where n is your number of quadrature points. We pass it into a neural network as a single pass, and we obtain the gradients of all the solutions in a single backward pass. Now to calculate the residual for each of the cell, what we'll do is, we will reshape this gradient matrix, which contains the gradient of quadrature points in all cells, into this shape, which is n element cross n quad, so that now you have a reference gradient matrix, and you have a actual solution gradient matrix, which is of shape n element times n quad. Now we will also have a Jacobian matrix, which is of the same shape as n element times n quad. Now we will element wise multiply with this matrix to get this representation. So what is happening here is that we have tried to eliminate the cell looping by concatenating all the inputs, sending them through the neural network once, and computing the gradients of all the problems, or all the elements in the cell in a single go, which eliminates the need to do this calculation repeatedly for n cell times. And here, using this, we should be able to compute at least one component of your loss in a single matrix multiplication. So this is, let's say, like if you take a 2D Poisson equation, you have your X component and your Y component. This is just the representation to how to compute this integral term in your X component alone. So similarly for Y component, you will have a separate dou V by dou X matrix saved in the reference gradient and your corresponding Jacobian matrix saved, which will be multiplied by your gradient in your Y direction. So this kind of actually eliminates the problem. And think of it, instead of solving for 100 cells looping over it, we should be able to solve in a single go, which kind of reduces your training time by a lot. Okay. But this is the algorithm that I was talking about. So previously, when you write the pseudocode, which I showed it in the previous slide, now it becomes that like this. So you just take the quadrature point in your current domain, entirely stacked together. You get the output, you get the gradients for everything, reshape them. You do a matrix multiplication operation with your pre-saved gradient matrix with your current solution gradient matrix, point-wise or element-wise multiplied by your stored Jacobian, and then you will get your components, your PD residual in, let's say, like 5-6 lines of your code. Okay. But this again comes back to does not address one more limitation that we saw before. As I told, this optimization was possible because assuming that our cells are in this way non-skewed, which have a constant Jacobian across an element, which enables us to do like, let's say, a vector multiplication to a matrix, which can convert the reference gradient to an actual gradient for a given cell by just multiplying with the Jacobian vector. But if you look at a skewed geometry, the Jacobians for the cell will vary at every quadrature point. So you won't be able to do this transformation on that kind of thing, which means we have to go back to the drawing board. In sense, like we again get back in trying to save the actual gradient matrix. So instead of saving one reference gradient for all cells, we have to now save the actual gradient, test function gradient for all cells. And again, we have to do cell looping. So what we understood is that when we try to somehow stack all these test function for all the elements, if you can see in this direction, okay, and rearrange your gradients in a certain way and perform transposes, we should be able to use some form of a tensor matrix operation to compute the loss in a single go, even for a complex geometry, which will have a different test function matrix for each element in the set. So this is how we move from a matrix operation to a tensor matrix operation, because the core limitation in your matrix implementation is that your Jacobian remains constant, so that you should be able to transform your single matrix of your reference into an actual gradient for all domains. But since you cannot do that on a complex geometry, you do stack all these actual computed gradients along your n element axis. You perform some transpose and rearranging operation, rearranging in the sense just the rotating the your matrix alone. So then you assemble your n element cross n quad solution matrix, which is obtained from the neural network. Then we can get the PD the one component of your PD residual for that particular component for all the cells on all the quadrature points in your domain. So this is the core idea behind our optimization, where we try to overcome the two main challenges in trying to address a method to have ability to handle complex geometry, but still have the advantage of not having to depend on the number of cells as a blocking factor in trying to obtain the training speed. Now, so far so good. Now we decided to try to evaluate FastVPINNs in comparison. So the left-hand side plot that you see is something called a local conservation, which means each cell will have a fixed number of quadrature points, and you keep increasing the number of elements along your x-axis for variational pins. However, so similarly, the number of quadrature points will also improve because the number of quadrature points per cell is fixed. So the blue line is the result from NVIDIA modulus. So we decided to use NVIDIA modulus library as a comparison for this particular problem. So here you can see that our variational pin frameworks better have slower execution times for both floating point 32 and 64 operation when compared to conventional pins with, let's say, 30,000 quadrature points itself. But in pins, it's collocation points. But you can see the main difference that we wanted to achieve at the start, which is to compare the performance of your actual HPV pins at, let's say, 1,200 cells to your method at 1,200 cells. And we could see that you can achieve a speed in the, like, let's say 100 times of speed up, because you are eliminating that linear component within your training loop. And the one curious question that arises, like, how a framework with these many floating point calculation in order to try to, let's say, compute numerical integration and stuff, which obviously for a lot of floating point operation can beat pins in terms of execution time. We think the main idea is the fact that your variational pins framework does not need to compute the second derivative if you transfer one derivative from your solution to your test function, which obviously played a major impact in this kind of test. And here
Thivin, I have a question for you. Why don't you transfer? Why don't you integrate one more time? Why don't you transfer both derivatives?
Okay, yeah, I will do that, Professor. Yeah, now that I think I will do that comparison study once.
But you haven't done it, right?
No, we haven't done. So we try to solve it with that particular variational form of the loss, because that's what we generally use in FEM. But I think it makes a good point. I will also do one comparison in trying to see how the second derivative calculation, if it is being performed, how it
because you will be pre-computing also everything, right? So then no derivative.
Yes, the solution, the second derivative of solution, we won't be pre-computing. That needs to be done there. So yeah, that will take some additional time. But again, so as long as it remains within the vicinity of prints, so it should be a good method. But I think I will try to do this comparison, Professor. Okay.
Okay.
So, the right-hand side graph you see is a global conservation, which means, like, let's take 6,400 points, but you put it in one cell and you put it in 400 cell, and you could see it is almost constant for FastVPINNs because the calculations are completed in a single go. But however, the existing implementation of VPINNs, it's linear. It's appearing like this because the y-axis is log scale, but the trend is linear when you look at it for the current implementation. Okay, so we try to solve 3 different examples with variational pins and try to get these solutions. So this is the accuracy when compared with pins versus VPINNs. So what we did we took 6,400 quadrature points. We kept all the parameters constant between pins and variational pins. Let's say number of boundary points, number of interior points, the collocation points for this thing. The only thing that we did is that if it is a 2-pi problem, which you can see here, if it's a 2-pi problem, we will take a 2x2 cell, which means each cell will have 1,600 points. Similarly, if it's a 4-pi problem, we'll use 4x4, but we'll ensure that the number of quadrature points on the global scale when compared to pins and VPINNs remains same. So here you can see that VPINNs, which is in green color, always achieved a mean absolute error, which is some magnitude less than the counterpart pins. And in the right-hand side, we have provided the training time for pins versus VPINNs when trying to compare for, let's say, a higher frequency problem, from lower to higher frequency problem. So here you can see for like the green color line, which represents pins, tend to reach the desired tolerance much faster along the x-axis, which is time, when compared to your pins counterpart. So in our case, in this case, I think the 8-pi case with soft boundary conditions, we were able to reach this in 40K or 50K epochs for VPINNs, but it took close to around 250K epochs for pins to converge to that particular solution using soft constraints. Okay, so this is the performance aspect of it. Obviously, we wanted to compare both the accuracy and training time to see how well it performs. And this graph shows
I have a question. Thivin, I have a question also here. So there is a version called separable pins. You've seen that, right? From the Korean separable pins, which is basically tensor pins.
Okay, Professor.
So you have not compared with them, right?
No, Professor. We compared it with
separable pins in the strong form,
okay.
but I think this is a 2D problem. So for 2D problem, probably you have I think they claim a factor of 10 speed up compared to pins.
Okay, Professor, I will try to.
For 3D and time, it could be like 60 plus times in terms of,
Okay.
so it's called S-pins, separable pins.
Okay, Professor, I will try to do that. So, okay. Yeah, so we just wanted to establish a benchmark with pins. So I think we went with naive pins. I think now, given that we will do more experiments on the other implementation of pins as well, just to see where we stand. Okay. So for forward problems on complex geometries, so this was our objective too. So we created this mesh externally from Gmesh, which has close to 14,000 cells. We try to solve the problem with 350K quadrature points and 6,000 boundary points. We used a simple architecture of 50 cross 3, a learning rate of 0.005 for 150 iterations. So current implementation of HP VPINNs will not be able to handle because it's written for uniform geometries, but based on the time taken on the cell looping thing, it would have taken at least, let's say, 1 week or so to train this problem of with 14,000 cells for 150K epochs. But the current implementation in an A6000 GPU, we were able to solve this within 35 minutes. So then we moved on. We showed some example of inverse problem. We showed the example for 2 different inverse problems, which is spatially invariant.
Did you tell us, did you tell us what problem is this? Just Poisson equation on a complex geometry or something else?
I forgot to mention. This is a CD2D equation, Professor. This is a convection diffusion.
What is it?
Convection diffusion
Advection
problem.
diffusion.
Advection diffusion problem.
Okay,
yeah.
Sorry, okay.
Sorry, I forgot to mention it here. Yeah. So moving on, for inverse problems, we try to solve both the things. One is spatially invariant and spatially variant, which means like in a spatially invariant thing, let's say you are trying to predict an epsilon in your Poisson problem, then you can just create one trainable variable. However, we have a spatially variant when your epsilon itself is varying with respect to x and y. You generally ask your neural network to predict that epsilon. And how does the neural network fit this is because you add a sparse data as one of the laws to your neural network to train, due to which it also learns that parameter too. Okay, so this is the example for a Poisson problem in predicting an epsilon. Again, it's a 30 cross 3 grid with number of 50 sensor points. We used a 2 cross 2 grid with 40 quadrature points per element. The initial guess was taken as 2, where actual element was 0.3. It reached a required convergence of epsilon at close to 2000 epochs itself, but we had a tighter tolerance of 1e minus 5. So it reached at 9000 epochs, which took close to 18 seconds. Okay, so then again, we wanted to show our ability of a method to solve inverse problems also on complex geometries. So we took a circular domain, meshed it with skewed quadrilateral cells. We tried to solve advection diffusion problem with a spatially varying epsilon value. We took these parameters, where this is the actual function of your epsilon. And these are the parameters that we have used. Again, a simple neural network architecture. I think the learning rate is wrong here. It is supposed to be 5 into 10 power minus 3. So let's quit here. And we use 500 sensor points. And we were able to achieve an error of 1e minus 2 for both your FEM solution and the predicted epsilon value. Again, on an A6000 GPU for 100K epochs, it took around 200 seconds for this to solve. Okay. So again, so one question that arises is the fact that it cannot be the case that for any number of elements, it is going to be a straight line, because it cannot say that for if you keep on giving 14,000 cells, it is going to retain your straight time. So what we're interested in doing is trying to understand which of the hyperparameters affect our training time more. So we pick 3 main hyperparameters, which is the number of test functions, number of quadrature points, and number of elements. So these are the 3 combinations that we have tested by keeping one of the parameter as constant. So in this case, it is number of cells versus number of quadrature points and their time taken. You can see that after a certain point of time, everything increases. But again, so if you look at where they increase, so the quadrature points and all, it's after 20,000 quadrature point until it maintains a constant time. And even for cells, if you look at it until 100 or 200 cells, it almost remains the same given your number of quadrature pointers. If you tend to increase for each cell, you try to put 100 quadrature points, then yeah, again, there's a trend that you can see here, which increases based on your number of quadrature points or test functions that you choose. But again, we wanted to push the graph to the other side to see that, yes, this is how it scales for different parameters. And we did realize that the number of quadrature points is one of the most affecting parameter when come to the comparatively to other parameters. This is because when you do the tensor matrix operation, the reduction happens along the quad direction. So you have n test n element and n quad shapes in your tensor and your gradient matrix, but the resultant will have only your n test cross n element because the reduction happens across your quadrature axis. So that's why we think that the parameter is high. Okay, so I will quickly go to the library implementation. But before that, I would like to say all the results that I have presented here and in the paper are available for in the documentation, which I'm going to show now. So one more thing is that we wanted to not to just stop here as a research work. We wanted to create this as a package so that a lot of people can also explore it. One good motivation is that, see, a couple of years back when we started learning pins, I think we came across the DeepXD library, which made our life very easier when trying to, let's say, trying to solve different kinds of problems as fast as possible. Just like you get a problem in mind, it's very easy to write a code for it to solve and in such thing. So we wanted to create some kind of an easier package where people can train different PDEs for different boundary condition or different types of problems as easily using a minimal amount of code possible. Because if you look at the implementation of the code, the current code that is there, you will see like 400 to 500 lines of code, which can be very difficult to, let's say, modify if you have to solve for different PDE or different boundary condition easily. And especially if you have to solve for complex geometries. So we wanted to create an interface-based Python library so that we can be able to do that. So we created a library for a PyPI package as a PyPI package. So people should be install this library by just using pip install VPINNs. This code has all kinds of quality assurance check, where we have tests like unit tests, where we check each module, and integration tests are where you try to solve a PD and make sure that it reaches a certain accuracy and only then it passes. And then there are a lot of tests like compatibility tests so that it ensures it runs on almost close versions of your Python and your different operating system and so on. So currently, as per the metrics from Code Curve, we have 96% of test coverage. And one thing that we are like feeling good about trying to write this library is that you should be able to solve a simple Poisson 2D equation with less than 6 API calls to the library. So if you see the library is split into these modules, your geometry module will take care of all your, let's say, internal or external mesh calculation. You are rearranging your edge points if you have to calculate your normals and stuff. Then you have your finite element module, which hosts all your test function quadrature points, and it hosts all your bilinear or affine transformation, which is used to get your values from reference to your actual, and it also assembles element-wise matrix. Your data module is where it begins to convert it into an actual tensor. So let's say if you want to do this implementation of PyTorch, all you need to do is change your data module and from all these modules, because until here, everything is in NumPy. And this is where, let's say, 80% of the work for your library comes into it. Then after that, you convert your data into the tensors, required tensors, and your physics module, which has the loss functions in the tensor notation that we have seen before, and your model class, which kind of handles different kinds of problems. And this is frankly the code that can be used to, you just create a domain for your geometry, you get your cells and boundary points, you create an FE space, which is responsible for, again, this FE space comes from our in-house finite element package called Parmoon, which is written in C++. We just use the term here. It handles all your finite element test functions, shape functions, quadrature routines, and everything. You get your forcing function. You have your data handler, which converts everything to a tensor. You pass it to a model with all the parameters, and you can just go ahead and directly train it. So this is the same code for every kind of problem. All you need to do is give different boundary condition in different problems, and that should be it. Okay, so that's where we show our documentation. So where we have, so let me try to show, okay, let me discard it. Let me quickly show you the documentation page of our library. So here, whatever the examples that we have put in the paper is available here for people to, let's say, run on it, including the complex geometry. All the files required for it are present here. So let's say if people want to run complex geometry on a gear, all the code required for it and the explanation is available there. So people should be able to find it. And this is how we have given the values are. So let's say if you have to solve a complex problem on solve a convection advection diffusion problem on a complex geometry like a gear, you need to set up an example file which will have all the boundary conditions and the values, your exact solutions and your bilinear parameters. You have an input file which defines all your, let's say, number of cells, number of quadrature points, what kind of FE order you have to use, what model architecture, learning rate, and everything. Then you should be able to call your normal routines and try to solve it. Okay, so that ends the all the discussions that I have made in the paper. So I'll take a couple of minutes to just quickly introduce what are the future works that we are trying to do, because the reason why we started improving this application in the first place was that we had and a different application in mind to start with to perform with FastVPINNs. But we realized that the training is slow. So we did all this to make sure that we can use this framework to just explore different problems. One such problem that we explored is for incompressible Navier-Stokes. This is currently accepted to ICCFD. So for that example, we solved lid-driven cavity for Reynolds number of 1 and for Coasny flow for a Reynolds number of 40. Again, so I think this, to the best of my knowledge, is the first implementation of a variational pins framework for any vector valued problem. So we have we had solved it for Burgess in 2D for a vector valued. Then we solved, just to give a proof of concept that we can proceed in this direction, we decided to solve the Coasny flow for a given Reynolds number, and we were Coasny flow and redundant cavity, and we were able to achieve this results. So yeah, this is our team that currently works on the scientific machine learning, especially FastVPINNs in our lab. It's myself, Professor, myself, and Divij Ghosh, and Mahesh Tom is also working on some of the applications of FastVPINNs that we have discussed about in terms of time-dependent problems and so on. Okay, so yeah, that's it. I hope I didn't bore everyone out more than the time allocated to me. So yeah, now it's time for questions. So if you have
Hi, Thivin. Thank you so much for your nice presentation. And don't worry, your timing is perfect. And also, if you need a few more minutes, if you want to say something else, please take your time.
I think I started rushing 10 minutes back. I said whatever I wanted. Thank you.
Okay. That was a really nice talk. You did a lot of work. Thank you so much. Do we have any questions from the audience? In the case, maybe I can have I can ask a question.
Exxon can ask a question since it's his work.
Yeah, I actually have a few questions. Well, first of all, this is great work, and I'm glad that the issue that we were facing with developing this code is being resolved. Well, I wanted to first ask, like, what is the version of the HP VPINN that you're comparing your result with? Because I think this is the one that's on GitHub.
Yes.
Okay.
Sure.
Yeah, some of the results that you have in the comparison make sense, because I actually had some of the vectorization that you had as well, but this was not on the GitHub repo. But it's good that it's actually you're putting it in a good implementation here. Another question, what are the test functions that you have for all of these cases?
Okay, so in all the cases that we have used, we use the special kind of the Jacobi polynomials, which is J of n will be J of n plus 1 minus J of n minus 1, which is used in the code that is there on GitHub. So we used that. We didn't explore much on the test functions used. We generally used what was mentioned in the existing repository.
I think Exxon you used Legend, right?
I had Legender and Chip. Oh, so you used Legender, right?
Yeah, I think it's legendary. Yeah.
Okay.
If the order 0 is Legender, if it's
Yeah.
-1/2 is Chebyshev.
Yeah. Did you ever try on higher dimensional physical problem? Like, because you have the results only on 2D.
Yeah, so I
When it
did
goes to
start
3D.
Yeah, I did start the implementation. For uniform grids, it's straightforward, but I've always wanted to, let's say, put out something if it works only for, let's say, a sphere or something on a 3D, which becomes difficult because it involves writing something like similar to an FEM framework. I think for uniform grid, I have results in 3D for scalar problems. Yes.
Okay.
Yeah, the challenge is here we need to have this transformation, right? When it go to the trilinear, if it's a tetrahedral or hexahedral meshes, right? Because when it go to the complex geometry, so that has to be transferred from our FEM package, that has to be transferred and then to the Python and to take care of it. But in principle, yes, it should be done. But of course, the complexity goes exponentially when you increase the dimension. It is not like a 2D and then the 3D is straightforward. That statement cannot be made, and when it comes to the implementation.
No, that's true. It's true. Yeah.
Especially when it comes to complex geometry, as I told, my target was that, so that it should work on any mesh at least. So trying to the cell data structures, edge data structures everywhere, that is a task. It's going on. But to answer your question, for quad cells in 3D, uniform cells, I think we have got results for scalar problems.
I have one more question if no one else has questions.
Yeah, please go ahead.
What is the size of the network that you're using, for example, for that gear example?
It's 50 cross 3. It's 3 hidden layers with 50 neurons each.
Okay. That's okay, so you have the architecture.
Paper, the lower architecture works well, at least for scalar problems. And the lower number of hidden layers works well for a scalar problem.
And you have one single network for the entire domain that you have, correct?
Exactly. Yes. One single network. Yeah.
Okay. All right. Very impressive results. Great.
Thanks. It means a lot coming from you. As I told, we have been like, we should have looked at the paper like n number of times when we have to do this implementation. Feels nice to like talk to the person who actually wrote the first version of the paper.
Maybe Raj, you have any comments?
Yes, I do. Yeah, I do. So it's very good work, Thivin. It's really impressive. Can you go to slide number 21? The slide number 21.
Where do I have the slide number here?
Yeah,
Yeah.
Can you explain this part a little bit more? Like what exactly you're doing in this part?
Okay, let me
Slides.
just go. Yeah, sure. Let me just take a pen. So if you remember here, this algorithm, wait a minute, let me try to come to this algorithm. This part of the algorithm was understood, Raj? Is it fine?
Yes, this is fine.
So now, in a complex geometry, you cannot have a single vector of a Jacobian that when multiplied by your reference matrix can convert your reference gradient into actual gradient for a given cell. Correct?
Yes.
So you had to stack your tensors. So you have to go back to calculating actually the gradients in your original domain. Then you stack them, okay, along this axis. Then you perform multiplication. This is tensor matrix multiplication, which is similar to a matrix vector multiplication in a higher dimension. You will reduce along a particular dimension. So in this case, you use a normal, in TensorFlow, you can just use matrix vector itself. You can use MATVEC, that function, and pass in this tensor and pass in this matrix. You will get your final residual matrix in the shape of n test, n element, since it is reduced along your n quad axis. You can also do it in einsum too. Like let's say like IJK, KJ equal to IK or something in such a sense. I think if you have to do it in PyTorch, you have to do it in such a way. Okay. But in TensorFlow, that actually by default happens when you use a matrix vector routine. So I just used it.
Okay. So it's just like the same routine in the TensorFlow, right? That if you store in this form, it will. So basically, it vectorizes towards the dimension of quadrature, right?
Reduced direction of quadrature. Yes.
Okay.
The point is here compared to the previous one, right? The Jacobian changes to quadrature point, right? And then the dimension increases rather than having like one particular value. Apart from that, the idea remains the same.
Yeah. So in this case also you store Jacobian on GPU, right? Pre-computed Jacobian, right?
Yes, we tend to like pre-multiply it. Yeah. So exactly. So you also have a corresponding Jacobian matrix here, which will also be multiplied with your gradient.
So this will be hold unless otherwise you are going into the concept of moving meshes or deforming meshes. Right. If you are solving anything in the direction of moving meshes or the free boundary value problem, then the Jacobian changes. Then this trick we need to come up with some other implementation then.
Yeah. So for the larger domain, so the size of Jacobian is like number of quadrature cross number of elements. So for larger domain, so there was no memory hindrance, right? Like from the GPU side, because
correct.
sometimes like computing that on the fly is much more efficient than storing it for.
So that's the trade-off, right? But then we have to think maybe then we have to go into the lower precision kind of thing. All these things we can explore and then see the accuracy and so on, right? So there is no free lunch at the end of the day.
Yeah, exactly.
We have to compromise.
At least we explored. We took the pre-computing approach.
Yeah, exactly. Because some of the implementation in GPU for DG I've done, I compute it on the fly because for DG this is very small. It's a small matrix, right? So this is the.
Makes sense.
So just the one suggestion I want to give. So can you go to your performance plot?
Performance plot?
Yeah. So something surprised me here. So from FP32 to FP64, you don't have much improvement. Why it is so? Like it's usually like pretty. GPU is not good at FP64, so FP32 should have a much more better.
You're saying that the difference is not large enough?
Yeah, difference is not large enough. Why? So
I think again, we are looking at a domain with just 30,000 points. I think this effect will keep scaling if you go to 300,000 points or something.
And also we have to see the scale, right? Maybe it's a compressed. Probably we have to plot only these two separately, and then we will be see whether there is a
it's a factor of 4. I think it looks like a factor of 4. 3 to 4.
Yeah, it should be here. 2 or 3. I think I will send out put out the actual value somewhere in the documentation.
The scaling compression issue. Probably one has to plot it separately, and then you will be able to see exact difference.
Yeah. Okay.
Yeah.
Okay. Also, you can try with TF32. You can see that it will be much. Then in that case, you will be using tensor cores TF32, not float point 32. It's a TF. So in that case, you will use tensor core of GPU. So your number will further go down the compute time. So
I think I misled it. This is TF32, TF64. TF.float32, TF.float64.
No. That is still float 32. It's a TF32. Just Google TF32 TensorFlow 32. So it's a TensorFlow 32. TF.float 32 is a float 32. So they have the same dynamic range, but precision is cut actually.
Yeah, that actually good idea. I will give it a try on this.
Yeah, sure. So your number will further go improve. By the way, very good, impressive work. So thank you.
Raj, here they use the Blast GPU. I wonder if this is not the Jim Demel version, right?
No, so for GPU there is a cuBLAS, like CUDA BLAS. So I think that is what he meant to mention. He meant actually. So BLAS is for CPU, and the NVIDIA developed cuBLAS actually. CUDA BLAS.
Is that what you use, Thivin? You use the CUDA BLAS?
Yeah.
Okay.
TensorFlow by default on the backend uses cuBLAS as its routines to So when I call from TensorFlow, it generally uses the BLAS routines by cuBLAS.
Yes, so, but that is different library, not the BLAS one, right? So there is a cuBLAS. That is cuBLAS.
Okay. Any other questions?
No, it's I'm good now. Thanks so much.
How about JAX implementation? Suppose I go and implement this in JAX. Would I beat you or not?
I think so. I'm starting to think like everything is moving towards JAX. It has inbuilt vectorization. But as far as I can see, the core idea or the logic relies on training the loss calculation that you do in tensor form, which is already in your efficient blast routine. JAX is very good at distributing tasks and like doing it coherently. But given that you have assembled everything and the only operation is pass these tensors and calculate the loss in a single go,
No, but
I will
also the
say
derivatives, the derivative
those.
evaluation.
Oh, okay. That okay. Yeah, might be. Yeah, it will beat in that case. Yeah, it can be a little bit more efficient.
What do you think?
Yes,
Yeah,
that's
yeah. I
if
think it will improve, further
if
improve. Yes.
JAX routines to compute gradient is faster than TensorFlow's routines to compute gradient, then the only difference between a JAX and your TensorFlow code that I have is the way in which the gradients are calculated. So if there's a good claim that JAX will compute the gradients much faster than TensorFlow, then yes, it will improve the speed up of the current implementation. Sorry, Professor, was it clear? Sorry.
Yeah, fine.
Yes.
Great, Thivin. Thank you so much for all your replies. Do we have any other questions from the audience? It looks like we do
I have
not.
the last question for Thivin. Thivin,
Yep.
what year are you? You're a PhD student, right?
Yeah, Professor, I'm about to complete my PhD.
What year, are you? Third year, fourth year, second year?
I'm fifth year.
Fifth year.
Yeah.
Okay, so when you complete your PhD?
I think in a couple of months or in 3 or 4 months, I should be able to complete it, Professor.
Okay, I'll be happy to hire you as a postdoc.
That's one thing that I wanted to hear before I joined this call. I don't know how to react. Now, thank you, Professor. I will apply to the lab.
So
Yeah,
happy to
that's what
host you here and start collaboration with Professor Ganesan.
Yeah, in fact, one of the today, even though I agreed to present, right? He's very keen. He said, okay, maybe the result section I want Thivin to present, but it happened incidentally that my internet went off, then the presentation entire thing, whatever happening for good. This is what I always say, that it's good to hear that.
I was very impressed, and I usually not very impressed. People know that, but I was very impressed with Thivin. So he'll do very well.
Yeah.
Thank you. That means a lot to hear it from you. Thank you, Professor. Yeah, so I can't speak. Anyone has any questions?
In fact, he's having a very good offer from one of the companies, and unexpected, more than my salary, double of my salary offer he's having. But but I insist him to take an academic position rather than the industrial offer. But we have to see. I will talk to him tomorrow and then try to push him towards academia more than the industry. He can go to the industry after postdoc or joining there as a faculty, but
Yeah.
Up
So I
to him,
always
but I'm
contact
happy.
him.
I'm happy to host him here if
Thank you.
he wants to migrate.
Yeah, I'm seriously thankful, Professor. I will apply. Sure, Professor. Thank you. Yeah. Okay.
Okay, great talk, Thivin. And in that case, I think I'll see you soon around here. Yeah. Do you have any other questions from the audience?
yeah, maybe one quick question to Professor Kaneda is, so where do you think that the field is going to go from now on? But I see a lot of potential. There are a lot of criticism, but I'm against that, right? This is an emerging field. One has to really try it out. And then we have to come on, definitely, like, I see a lot of potential, especially when it comes to the implementation to the GPUs, where we had a lot of tough time when we to port our FEM code to the GPUs, but this is a natural way of taking to the GPUs. So one quick comment, what's your impression, so that we can also look into the directions?
I think there's a lot. I think what you're looking at, speeding up robustifying and speeding up this type of methods and extensions is very important. So I think you're looking at the right. That's why I said maybe Thivin can also look at separable pins, because we had that Korean group also here. They gave a talk and they were also very impressive. Just took something that standard pins and increased it by almost 2 orders of magnitude, and especially in high dimensions. So works for not all problems, but it's actually, but then robustness for forward problems. I think for inverse problems, I think that everybody wants to use pins, but for forward problems, I think
we have to.
Yeah, a factor of 100 is great of a speed up. Then you compete with finite elements, and then given the fact that finite elements cannot make use of data, then pins is the winner. For inverse problems, I think that the winner is already pins, but for forward problems, I think speeding it up and that robustifying it, correct. I think you're looking at this at the right question.
Yeah, thank you.
Great. Okay, great. Thank you everyone for your time today. We only had one speaker today, so we will close the seminar. But I hope you have a great weekend, and see you next week.
Thank you.
Bye.
Thank you. Bye.
Thank you.